Thank you, Professor Chaudhary, for your introduction. And at the outset, I would like to thank the Academy for giving me this opportunity to speak on molecular machines. Previous three speakers, they have talked about biology and physics of molecular machines. So in this talk, I'll focus on chemistry. So a chemist view on molecular machines. Now what I'll do today, so I have divided my talk in two parts. So first part, I will give you the how these molecular machines has introduced in the chemistry, and it's all the way from the beginning to till 2016 Nobel Prize by three persons. So that will take you the ups and downs of this development and all. And at the last, I will talk about some of our work which we have started a couple of years back at the Indian Association for the Cultivation of Science, Jadavpur. So molecular machines, so if we think, so actually it started, the first serious discussion on molecular machine was this by Feynman in 1969 talk in American Physical Society, that there is plenty of room at the bottom. So this is the first lecture, and what was the question? So the possibility of building small machine from atoms. So that is machine small enough to manufacture objects with atomic precision. So that was the questions, and lot of discussion were there, and he talked many things, top-down approach, bottom-up approach and everything. But later on, so after 1959, after 25 years later, he gave another lecture on tiny machines. So that is, how small can you make machinery? And he was convinced that machines with the dimension of nanometer scale is possible. And he gave examples, so we have already heard, we have seen so many animations, all machines are available in the biology. So he gave the example of bacterial fragile corkscrew shaped molecules. When it rotates, it moves forward. So that was, and he gave many other examples also. So he gave the vision in 1984, the molecular machines will exist within 25 to 30 years time. And that was his future vision. And aim of this lecture was to inspire the researcher in the audience, to get them to test the limits of what they believed possible. But interestingly, neither Feynman nor a researcher in the audience knew at the time that this kind of machinery has already started somewhere in some subjects. So what is that? So that is, we have to go back to 1953, is mechanical bonds in molecules. This gentleman, he was working in Bell Laboratories in the US. So that time, so mostly, so what do you mean by molecule? Organic molecule, all are by covalent bond. So covalent synthesis, people started, this chemist started trying to make molecule with chains in which ring-shaped molecules are linked together. So this will not only give the new molecules, but new kind of bond, which is called mechanical bond. So if you have this kind of molecule, another molecule linked, so it can move anywhere. So it is not only covalent, but you make molecule, another, you linked it. So the way you design, so you can make it different kinds of interlocked molecules. So that was the idea. So this like two rings are connected together. So you can call it a 2-catenan, and it can be different. Say one ring, you put one axle and put two stoppers, which the diameter is bigger than the diameter of this macrocycle. So it will not come out. So it can move any place. Then in this 1950s, 50s and 60s, many people tried. Say the researcher reported that their reaction vessel contained molecular chains, but it was very difficult to prove for them because yield was so low, there was no strategy that how to synthesize this kind of molecule. So yields were extremely low, and progress was regarded more as a curiosity than a functional chemistry. Then first report, if you see in the literature, this Edel Wasserman, he prepared the first catenated structure, 2 ring type molecule like this. And synthesis was like a statistical threading. Take a macrocycle and you take a linear rod, mix it together, and then you stir it in reaction vessel, then and then do some kind of reaction. So there will be some possibilities that this linear molecule will thread even something less than 1% or even less. Threaded molecule will be there, then you close this thing and you get the your catenated structure. This is the first example where he showed that during this process they could isolate less than 1% of this catenated structure. Later on, again, that was not very pure. Later on in his paper he wrote that after purification it is even 10 times less than that whatever they claimed 1% of yield. So that Wasserman first paper was statistical threading, but during that time this Frisch, who talked about mechanical bond, and Wasserman, both of them were working in Bell laboratories, and they started talking about chemical topology of molecules. So if you want to get like a ring molecule, 2 molecules can be besides and they can be interlocked, then topology will be totally different. So these are the concept of topological isomers of cyclic molecules is introduced sometime 1961, like an unknotted and this is a knotted loop. So molecular knot can be possible, or interlocked rings or non-interlocked rings. Many others like Mobius strip and all kinds of things. This is a very historical paper on chemical technology, topology. Then actually by directed synthesis, by proper designing, this is a person, Gottfried Schill from Germany, he took the advantage of covalent synthesis of this kind of molecule, and the final step he broke this oxygen carbon bond and carbon nitrogen bond, you will get this. But this is 22 step synthesis. It's a huge synthesis, but again is a kind of first directed synthesis of catenated structure, and then after that this rotaxane kind of molecule first synthesis in 1967 by Harrison. But all the cases, main problem was the yield of these compounds was very, very low, and people were frustrated and they stopped working in this field. The field remained dormant for long time. And in the meantime, that is, I talked about 1967, so there are another new chemistry like a supramolecular chemistry started coming, and these are the 3 persons who got Nobel Prize in 1987, Patterson, Lane and Cram. And they synthesized different kind of receptor molecule, and then molecular recognition came into the picture, and for there they got the Nobel Prize in development and use of molecules with structure specific interaction of a high selectivity. So host case complexes are introduced into this chemistry field. So this crown ether is developed by Patterson, and this geometry lane macro bicyclic krypton, and this is furan type of molecule. So I am not going details to this, but these came. 1967 is the first report, 87, 20 years time, molecular recognition area was very, very strong. So, and in Nobel lecture 1987, Geometry Lane gave this roadmap. So covalent synthesis, you get receptor, substrate, interaction, molecular interaction, you get supermolecule, you can get molecular recognition, transformation, translocation, everything. At the end you can see molecular and supramolecular devices. So chemistry point of view, this picture of molecular device came in 1987. Our Feynman told from 1959 and 1984, and field remained dormant after 1967. So then how to thread a string through the eye of a molecular needle, that question remained unsolved for a long time. Then one French group, Jean-Pierre Sauvage, he came up with a very simple solution. How to thread a molecule within a molecule. So this is again coming from supramolecular chemistry background. You can make a crown ether kind of molecule, and this nitrogen, nitrogen, and this is a linear molecule, nitrogen, nitrogen. You take copper ion, simple copper 1 oxidation state, take as template, then it will like tetrahedral complex like this. So 2 bond will come from this to nitrogen, and 2 from this, it will be threaded, it has to thread. The almost quantitative yield of this threading step, and you get the OH extruded from this side, and this is threaded structure. Then how he came with this idea, this background of his discovery for students only. So this, he was a very interesting story with this first krypton which Geometry Lane got Nobel Prize. He was a student in his group, and he is the co-author of that paper as a PhD student. And this new thing he gave, he got Nobel Prize again as a mentor doing this rotaxane chemistry. So in his independent career, he was doing photochemical cleavage of water to hydrogen and oxygen using ruthenium bipyridyl complex. Then in that time, this he is from David Macmillan from Purdue University came for sabbatical leave, and he was doing copper chemistry. Then he told Subhaj, so this is costly, so you should you should change ruthenium to copper. So then they started working on copper chemistry, photochemistry of copper 1 complexes with phenolphthalein type ligands, and they prepared this compound, and this was published in 1983 ChemCom paper. So that is the first this kind of molecule. Then Subhaj shifted to this kind of concept. Let's use this thing for rotaxane catenin synthesis. So he used these things, and this and this. You don't have to go through this. This is a strategy. The macrocycle, this copper 1 template, it will thread. So you have got functional group. The another 2 functional group, it will link. This copper 1 you can take out by some kind of a potassium cyanide or your cyanide. So it will come out, and you will get interlocked molecular system. So using this kind of thing, he has made large number of catenated structure. And another strategy he gave, so let's take this one and do double cyclization, this side to this side and this to this. You will get this kind of thing, and using your Cation, you can take out this copper, and you get completely interlocked systems. So these are the 2 strategies he has introduced. Now this is not only catenated structure, so many such kind of complicated structure he has prepared, like say how to make molecular knot. So you take this one molecule, this 2 nitrogen center, 2 nitrogen center, 2 copper templates, and another molecule will go this way, this way, this way. So you get 2 nitrogen here, 2 nitrogens here, copper, copper. So you get this situation. Now this OH, this molecule OH, and whatever it will extrude, that will form another molecule. So it will join here, and this side you join, you get this kind of structure, and you take out the copper by Cation, you get knotted structure. So actually these are the topological isomer. This actually 86 member macrocycle ring, and this is a knotted structure, and it looks like this. So and you can see the DNA trefoil knot also looks like this, so it has relevance. And later on he moved all kinds of Solomon's ring, Borman's ring, so lot of topological chemistry they have done by this Sauvage group. Then in 1991, Fraser Stoddart came into this area. The first report by Stoddart, this template host case chemistry, as I mentioned, this electron deficient molecule and electron rich molecule, they will just, this side is open, then this is the template is electron rich. If you mix this together, then it will just thread, and here you close it. So you got around 70% yield of this kind of interlocking system. Then all kinds of, like say, Olympic rings, and like 5 rings they connected together, they got Olympiaden. So in 1994, and 94 to 2013 there are many complicated structures, not only catenated structure, rotaxane structure they prepare. Recently they have introduced like a radical templation, which has very rich chemistry, so I am not going to discuss all these things. So this is from Stoddard groups. Now, once you get this interlocked molecular system, so how it will act as a machine? That is the question. So concept of machine can be extended to the molecular level. So already a previous speaker they have talked. So you need some kind of output, and if you give the input like external stimuli, and you get molecule will act like some rotational or translational motion in this case. So first such kind of movement in molecule was shown by Pradyut Stoddard in 91. So he made a molecule like this linear, this is axle, and both sides the stopper type of molecule. This is paraquat ring, and these are the two stations, say diphenol. So this is electron deficient and electron rich. So molecule will stay here because there is no covalent bond. So this kind of sometimes this molecule is here and sometimes this, because both the stations are same. So this is this, and you can they have detected that room temperature that 2000 times this is moving here and here by different solution NMR studies and all. So then they tried to change it. Let's move this station different, like a biphenol and you like benzidine. So this is the benzidine is different station, green color and red color. And in particular situation, like suppose if you protonate this thing, this NH, it will be NH2 plus. So then the positive charge will repel, it will immediately settle to this position. And if you change the pH, again if you get this like NH, it will come to this position. So you can control by controlling the pH this motion of this. Even electrochemically also one can do this settling effect. So for this kind of molecule. Interesting, Stoddard even went up like a molecular elevator. So this is again thanks to supramolecular chemistry. So this is like he developed this kind of molecule. So this is a crown ether type of molecule, your wheel here, and this is a platform. Based on this platform, you grow 3 wheels here, and this molecule with 3 legs. So and you have 2 stations. Here one station, another station is here. So if you make complex host-based complexation, so it will just thread. So this is the situation. So one situation, this is here, and another situation here. So they can, by changing conditions, so they can move this platform up and down 0.7 nanometer. So continuously you can do. So if you have some material, it can be entered here and then go to first floor, it will come out and it can do this kind of things. That was the concept. So this is by Pradyut Stoddard. And similarly, Subhaj, he introduced like copper chemistry. So 4 coordination versus 5 coordination. So you take 2 rings, here 3 nitrogen center, and in this case here 2 nitrogen center. So if it is a copper 1 situation, like this is a copper 1, so it will prefer tetrahedral geometry like this. But if you oxidize to copper 2, it will prefer your pentacoordinate TBP structure, trigonal bipyramidal. So it will, so if you take 1 electron out, so it will be copper 2. So this wheel will take a turn, and this will come out, and this will get in. So this is coming in. So you can take a rotation within the molecule kind of thing. So he has demonstrated it using the electrochemical oxidation reduction process. And again, we are talking about molecular muscles and all these things. So see, if you have this kind of molecule and this, here you have 2 coordination site and 3 coordination site, you copper 2 and copper 1, you can bring these 2 close and up like this. This muscle action within a molecule also one can bring by this settling effect. These 2 people, they were talking about molecular machines, and in the meantime, Ben Feringa, so his molecule was totally different, not like interlocked molecular system, and they were working on crowded system from 1977 or so. And first success came around 1999. So it's a molecule with two, like it is a rotor and this is stator and axial, and it can actually, if you give light, the 280 nanometer, so there will be kind of your, this kind of rotation all the time, but this is actually unidirectional. So biologists, what they told, that you need directionality. So you either right to left or left to right, because all the time molecules are moving, but how to bring the directionality within a molecule. So it's the first time they have demonstrated that you can do these things using, you put light, heat energy, so it is taking quarter turn each time. So first quarter, then heat second, half 180 degree, then 3/4 and then 4th. So 4-stage rotation he showed first time, and he calculated the rotation. The first molecular rotor was around, say, 1 rotation per hour, and then he developed a huge series, and now he has reached 12,000 rotations per second. So different kinds of molecule he has developed during this time, and he has implemented this thing, immobilized onto the surface. So when you put onto the surface, millions of machine on small place you can find out, or even you have demonstrated, say if you take liquid crystal, put this kind of molecular machine little bit and put a object 10,000 times bigger than your molecular machines, and if shine light, the machine will rotate, and on the surface this object is rotating. So he has like a demonstrated everything, and latest one is the molecular, this is nano car. So these are the 4 wheels, they are like individual rotor. So when it just rotate kind of thing, so this molecule just move from this to this way. That rotational motion to translational motion he has demonstrated in this work. So this 2016, they got Nobel Prize for the design and synthesis of molecular machines. And if we see these things in literature, all of them, they have kind of branded wheels. So the Subhaj, he used like a phenanthroline based, this nitrogen center, this kind of thing. Student is like a paraquat ring, electron deficient. Then later on other groups like hydrogen bonded ring and this. So when I think sometime 2010, we thought that we will also do some kind of work. So first question was where to start, because a lot of work already have been done by these big people. So we thought that we need our wheel to run the show. So we designed our wheel this way. So this is our wheel design. So previous slide, if you see, actually this is metal template synthesis, this is pi stacking, this is hydrogen bonded. So we thought, so we will make one wheel which will have all 3 properties, like here metal coordination site, pi stacking and hydrogen bonding. So 3 in 1 kind of template site, we have prepared this molecule. Then we started probing that can we thread this molecule. First thing that we tried to explore this trisamine, and most of the work that copper 1 by Subhaj is done by copper 1 template. So we preferred the 3 plus 2, the 5 coordination, so TPP structure kind of molecule it will form. So as a proof of concept, we took all small bidentate ligand and this, and we could show that yes, this is threading properly, this metal chelation, very high yield, and this is, you can see this metal temperature plus pi stacking in this region you can see. And we have done some kind of your selectivity study where we can see this copper fen, and this is the selective one. So our first paper came in this area in 2011. Then we thought, say we are threading 1 molecules, can we put 2 such kind of wheel in 1 axle? And we did something like take a fluorophoric acyl, here bidented 2 nitrogen center, 2 nitrogen center. So our idea is to put one wheel here, another wheel here. And actually we are successful, even we have shown by single crystal X structure also. Let's see, this is the wheel and this is a fluorophoric acyl. And later on we have done substitution. Can we replace this using like say association constant values and all? We have calculated everything and we have showed that we can even substitute this acyl by another acyl to get like a fluorescent on-off situation in this case. Then we are moving towards how to make a rhodoxane structure interlocked molecular system. So we tried varieties of acyl. This is our wheel acyl. We have started from like a bipyridyl methyl. Then we have increased the complexity like a ester group and bromide or amide, OH. Even at the end, if we have phenyl group, can we thread this kind of molecule within this macrocycle wheel? We have demonstrated, say all these molecules can be threaded, and what we started with the idea, can we get a template, this interlocked system using all three operative, like a metal templation, here you say pi-pi bonding and you get hydrogen bonding. So 3 template effects are operative in this particular wheel. So after that idea is to put stopper. So we have got wheel and this acyl threaded, we have increased the length, we have put different functionality, then how to put stopper so that then we can take out the copper and this will be inside this thing. So like this, 2 stopper. So this ring is in our case around the 30 member ring, so we had to prepare a bigger wheel, a stopper, and at the end we have azide for students, azide, and this we have acetylene moiety, so we can do click chemistry to click this stopper molecule with this acyl molecule. So this is azide and azide, and using copper. So first attempt was unsuccessful using copper as a template, because while doing click chemistry, it reduced to copper 1 and this was dethreaded. Actually we got this acyl with stopper and wheel was separated. So then we replaced this nickel, and finally we have got this kind of multifunctional rhodoxane molecule. So you can see now we have with us this kind of molecule. Here we can do metal chemistry. Here we can do anion chemistry. So many things can be done. So triazole, ester, bisamide or acrylamide, all are there. So we can do these things. And later on we have changed different wheel we have introduced, and to probe like say where it is going. So we have made it fluorophoric so that we can see that where this molecule wheel is going, moving. And then to make more complex one, from macrocycle to macro bicycle we have made, and we are using this as a wheel for threading. And first attempt we have functionalized this NH with acetyl group, and which is giving like a rotamer, because this amide is a carbon nitrogen single bond, so it will do like this. Some of this will be here and here, so you will get different conformers. So at room temperature generally you don't see this molecule is rotating, because it's a free molecule and this is thread, obviously it is rotating, but we are not able to detect. So when we attach this acetyl group, so we can see this NMR, so there are many isomer, and that's what it's showing complicated. And if you do temperature dependent study, you can see they merge. That means that time again rotation is fast. So room temperature it is like your rotameric thing. So we have shown rotameric kind of thing, and we have also later on showed that you can thread this like N oxide kind of thing, where like N oxide and here we have amide and amine. So in one state it is up, this nitrogen oxygen, it is binding here. Then if you protonate this nitrogen, it will down. So you are threading a molecule with a bicycle, and inside molecule you can do up and down, up and down. So you can do some kind of dynamic motion. So in summary of my work, so we have already showed this kind of thing. So macrocycle and this pseudo reduction, self-sorting, 3 pseudo reduction, axial substitution, reduction, multiple functional group, and we have shown this kind of dynamic motion and this all this. And this is my group. So the Subrata Saha, he started this work, and recently this Soikot Satra, he has submitted his thesis. Now these 4 persons, they have also joined in this work. So we are, and other people, they are working other work. And I would also like to thank the funding agencies for this work. And thank you all for your attention.
I'm not a chemist.
Okay.
I'm a mathematician. The operations that you're talking about seem to be deterministic.
Which, excuse me?
Deterministic, in the sense that they. But then, isn't there a stochastic component to any of these operations?
Yes, deterministic. Is there a stochasticity in it?
Like, Brownian motion was already in 1904, Einstein.
That's true, that's true. That's why I told that is a, now people are trying to bring the directionality within this molecule, and some people, they have already showed that by changing chemical functionalities, one can bring that one direction.
If I can just comment, in the beginning he showed that there are 2 stations, and in between, because of the Brownian motion, it goes back and forth, but unless energy is pumped in, you don't have on the average a particular one more stabilized than the other.
But the problem with Brownian motion is that it has a lot of parameters. And then, in order to, have the right one, you need to estimate the parameters.
Yeah, so people are doing, but we are not doing, but
somebody else is doing it?
Yeah, I think
Right.
say, this some group, they are working.
Okay, thanks.
Okay.
So you talked about finding a compound that can mimic muscle contraction, right? So can it mimic the movement to such an extent that we can help cure like muscle disabilities in human beings? Or
So all these are proof of concept experiment at this stage. So definitely it takes, I think, not less than 50 years or even more than that. So these Nobel laureates, they are telling maybe 100 years time you can get this in reality.
Any other question?
Ultimately, the motion of the molecule creates the heat energy, and do the heat energy affect the motion of the molecule?
Yes, that's what that Ben Feringer's work. First thing, he is putting light. I told you the quarter turn, and second step is that heat energy, which is converting another, because there is a carbon-carbon double bond, and it is breaking because it cannot double bond, it cannot rotate. So fraction of time that photochemical cleavage of one carbon bond, and then second step, it is taking the heat energy to take more moment. So that heat energy is taken by this molecule to take another turn. So they have demonstrated this thing already.
Okay. If there is no further question, let's thank the speaker once again.